Alright, class, this is a little different, obviously. Watching the videos of the notes as opposed to doing it in class, but this will at least give you an opportunity to kind of go at your own pace and uh, figure out if you're confused on something. You can rewind and watch it again, and then that way you have ideas on what you might have questions with when you come to class tomorrow. Make sure you fill out these notes in order to work on the homework at the start of class, and that way you're able to ask questions. Write any notes or questions that you have on your guided note sheet somewhere, so that way you remember the questions you had and you can ask when you get to class, and we can get going on the assignment. So today's section is about circles and arcs of circles. We've talked about central angles before with regards to different polygons, and that was just an angle whose vertex was at the center of the polygon. So much like those types of central angles, a central angle of a circle is exactly the same. This is an angle whose sorry with the handwriting, whose vertex is the center of the circle. I'll have to erase that as we get over to semicircle. But on our example up top here, on this circle up here, you can see angle APB is a central angle. The key is to have P, the center of the circle, be in the middle of our angle when we list that. Okay, so an angle whose vertex is the center of the circle. That's a central angle. That's nothing different than what we've done so far. Okay, a semicircle, I'll erase that. Hopefully you got that down already. A semicircle is, you probably are familiar with that, is half of a circle. Okay, so we would denote that with a symbol like that, with a arc, is talking about this half of the circle right here. That's arc AB. Okay, so that would be a semicircle since it's exactly half of the circle. More specifically, with semicircles, half the circle, but you get sometimes where you have arcs that are not necessarily half of a circle exactly, so we call those either minor arcs or major arcs. A minor arc is an arc that is smaller than a semicircle. So hopefully that would make sense, that a minor arc, being something is minor, that means smaller or less, that is less than a semicircle. A major arc, then, on the opposite, would be an arc that is larger than a semicircle. Okay, so if you need to pause that, I still can't write, that's too bad, but now you might ask yourself, well, if I'm looking at RS, I could either go this way, this arc right here, RS, or I could go all the way around here. And this one would be minor, since it's less than a semicircle. This one, on the other hand, would be major, because it's greater than a semicircle. Well, the way that we make sure we're going the right direction is by saying, if we want to talk about the major arc, we would use a point somewhere between S and R. So if I'm saying SR and I'm going that way, then I have to put that point in there that's in the middle. So STR would be a major arc. Okay? On the other hand, if I just said SR, then that's kind of implied that we're just talking about this little arc right there, since we're not throwing in that point T. So SR is a minor arc right here, and then STR, I'll draw that in green here, that is the major arc because that is greater than a semicircle. Okay? Alright, you can pause that if you need to write that down further. Make sure you're trying to get that down. I'm working on the handwriting here. So, example 1. What are the minor arcs of circle O? Usually we'll talk about, a circle A or circle O in this case, where O is the center of that circle. So, what are the minor arcs of circle O? Well, this arc right here, AD, that looks like less than a semicircle, right? So that would be a minor arc. And we know we're talking about this because if I was trying to go all the way around from A to D this way, I'd have to at least have one of these points listed in between there to make sure that I know I'm going that way. If I don't have a point listed, that means that should imply right there that I'm going from A to D in this direction. Another minor arc. You can pause it if you want and try and write the ones down that you see and see if you get it correct. CE would be another minor arc. Let's see. AC is also a minor arc, and then there's a fourth one, DE. Okay, so maybe you got that right, or hopefully you at least can see that all four of those are less than semicircles, and we know that we're going around. I keep stressing this, but we know we're going this direction since I don't have another point listed in between there. So you can see the minor arcs there. Alright, what are the semicircles of circle O? Well, those would have to be exactly half of a circle. So it looks like I have a few different ones here. I could go this direction. I could go this direction. And I could make a few different semicircles. So the first one I'll draw is ACE, that one right there. Okay. Then I will go, you can pause it again and see if you want to write down, see if you can get a few. EDA, it kind of looks like the same one, but that's related to that same semicircle. It's just using the other half of the circle there. Okay. So there are two left. Once we got those two, there are two left, and they're related to the other line drawn there. Looks like we have DAC, and then the other half of that would be DEC. Now, if you wrote this, for instance, as CED, that would be the same thing as DEC, so long as the two endpoints are the same, but they could be in a different order, and it still would be correct. All right. So those are the semicircles. Now, the last part of the question, or the example, asks us, what are the major arcs of circle O that contain point A? So first of all, keyword major, that means that it has to be greater than a semicircle, or greater than half the circle. And then we're worried about major arcs that contain point A. So see if you might be able to find a few that you might be able to get, but the first one that I see is if I go all the way around here, that arc ACD, that contains point A right there. Now you'll notice I didn't put ACED because once I have one point in between, that implies that that tells me that I'm going this direction as opposed to the other way. Okay, if you want to put ACED in there, if you want, if it spells something nice for you, go for it. But you just need one point in the middle, and that'll tell you which direction you're going. Okay, there are three more if you're trying to pause it and try and guess them, see how you do. But I'll continue here. If you want to pause the video, you obviously can. Another one that contains point A would be if I start at C and go all the way around to A. So CEA. That is a major arc because it's greater than a semicircle, and it contains the point A. So that's another one. There's two more here. The next one that I see is I just keep working around the circle is EDC. So once again, if you wanted to put EDAC or EAC, that would be the same thing as EDC, so long as the two endpoints are the same, and then the middle point tells you which direction to go. The last one that I see, and hopefully some of you are seeing it also, is DAE. That one, start at D and go to E. Those are the four major arcs. This one, if you put a B in there, that makes it kind of interesting for some of you, I'm sure. Alright, so now that we've talked about kind of how to figure out what arcs are and what's the difference between a minor arc, a major arc, a semicircle. Some of you already know a semicircle, but now we've talked about that, we want to kind of talk about how we figure out the measures of these arcs. A full circle, as some of you might know, the measurement of a full circle is 360 degrees, so that'll help us out when we're trying to figure out the measures of different arcs. So the measure of a minor arc, so an arc that is less than a semicircle, is equal to its corresponding central angle. And when I say corresponding central angle, that means you see this central angle right here, RST, this arc right here, RT, that's corresponding because you see the sides of the angles intersect the circle at T and intersect it at R, which forms that minor arc right there. Okay, we want to keep in mind a full circle. Hopefully this is a little more room for you to write than it is for me. Full circle is 360 degrees. Keep that in mind. So a semicircle would be 180 degrees. Alright, so to figure out the measure of arc RT, this is our notation that we'll use, and I'll erase some of this so you can pause it if you need to finish writing that down. So to figure out back to where we're starting, figure out the measure of arc RT, how we will denote that is M of arc RT with a arc symbol on top is equal to actually the angle of its, or the measure of its corresponding angle. So the measure of angle RST, which it tells us is 50 degrees. So just like we measure angles in degrees, we also measure arc lengths in degrees. Alright, so a full circle, the angle is 360 degrees, the arc length correspondingly is 360 degrees. So I figured out what this arc was. Now the question is that we can go from there is, instead of figuring out what RT is going this way, how about we figure out the length of RQT, that arc right there. Alright, and it's much like when you're doing angles where you're trying to figure out the size of an angle. When you're trying to figure out the size of an angle, if you have two angles that are put together, if you know one, then you can figure out the other one just by taking the whole thing minus that little one. So if you see what I mean here, the measure of arc TQR is equal to, what's a full circle? 360 degrees minus this little part right here, 50, and then all of a sudden I get 310. I get the measurement of this whole arc going, this major arc here around the circle. We know it's a major arc because the measurement is greater than 180. We know this is a minor arc because it is less than 180. So that's the difference between major and minor arcs. So like we just talked about, the arc addition postulate, it's on your theorems page that you'll be able to use for the test, and also your formulas page, but you'll be able to use both of those in case one of them doesn't have it. The measure of arc ABC, so ABC, some of you could try and draw that and see what arc we're talking about. That's the orange. I guess I already did it for myself here, making it orange, but that's okay. ABC is we're going that direction. Okay, so to figure out the measurement of that arc, what this postulate says is, if I take this arc right here, measure of AB, plus the measure of BC, Then if I add those two things together, then all of a sudden I have the measurement of the whole arc. So that's basically, we've talked about that with angles, we've talked about that with segments, so it's no different with circles and arc lengths. Alright, if you need to pause it to finish this, go ahead. Alright, so let's put what we've learned to use in those two formulas, or those two theorems, and see if we can. Alright, let's see here. Let's use some of those formulas and put those to use. So the first question is, what is the measure of each arc in circle O? So the first one is BC. So if we're doing this correctly, we would want to put the measure of BC, if we want to use correct notation, the measure of BC with the arc length over the top to tell me that that's what I'm talking about, an arc, is the same measure as its corresponding central angle. So right here, the central angle that corresponds to that arc, what's the measure of that central angle? 32 degrees. So I know that arc right there, 32 degrees. Okay? So let's figure out what's the measure of BD. If at any point you want to pause this and try and figure it out and then see if you got the answer correct, go ahead. I'll just keep on going that way. If you are not unsure of how we might get it, then you can watch it and maybe rewind and see if you can understand it a little better. Well, the measure of BD, the whole thing right here is what I'm looking for. I know this little part right there is 32, and I know that part right there is 52. So using the arc addition postulate, I can say the measure of BC plus the measure of CD is equal to the measure of BD. So I know that BC is 32 degrees, plus I know CD is 58, so I add those two things together and I get 90. So that angle this arc right here, is equal to 90 degrees. Alright, let's see, I'll erase a little bit of this. Just get that down, make sure you get that down. The measure of arc ABC. Well, since AC is, erase that a little bit, since AC is a diameter across the entire circle, then what I created was two semicircles. So if I go from A to C and go through B, the measure of a semicircle is 180 degrees. Alright, so keep in mind with that B right there, that tells me that I'm going that direction. Now in this case it wouldn't matter if we went this direction either, because that would semicircle they'd both be 180, but for other examples it's important that you know which direction you're going. The last part of this example, the measure of arc length AB. Well, that's what I'm looking for right there. I know if I go all the way to C, that's 180 degrees. So I want to take 180 minus this little part with the green, and then if I take 180 minus that little part, then that will give me the length of this arc right here, the measurement of this arc. So the measure of AB is equal to the measure of arc ABC minus the measure of arc BC. So I know ABC is a semicircle, so I know that's 180 minus BC is 32. So if I subtract all that, I get 148 degrees. Once again, if you are struggling on some spot, or you're not quite sure what the how something worked or along those lines, make sure you write that down or circle it or star it and write down specific questions you have. That way, when we get to class, you can ask me or ask someone who might have understood it a little better than you did, so we can kind of all try and get on the same page. Alright, we'll head on to the next section here. Alright, this part right here is something that you are all probably familiar with, at least have talked about before. Whether you remember it or not is up for your own personal memory. Some of you have, we'll continue. Circumference of a circle is equal to, and there's two different ways you might have learned it. 2 pi r, or circumference is equal to pi times diameter. So I think some of your teachers before are a lot more creative than I am. Have told you one way to remember it is cherry pie is delicious. So we get the C for there, cherry pie is delicious, which I agree. Keep in mind that 2 times r, 2 radiuses is equal to 1 diameter. So that's why these two formulas are the same. Whichever one you want to use or whichever one you're more comfortable with, go ahead and use that one. I don't have a preference one way or the other, so maybe you have a preference that you might want to use. Alright, let's look at example 3. A 2-foot wide circular track for a camera dolly is set up for a movie scene. The 2 rails of the track form concentric circles, which means one is inside the other one. The radius of the inner circle is 8 feet. How much further does a wheel on the outer rail travel than a wheel on the inner rail in one turn? If some of you watched the Final Four, you might have seen the camera angles where the camera's kind of going on a little rail system along the court. That's kind of the idea here, except instead of it going back and forth, the camera will go in a circular fashion around this circular track. So the radius of the inner circle, if we draw a picture here, and you want to draw a picture along with me, the radius of the inner circle is 8 feet. Alright, so we got that inner circle drawn. And then the track has a rail that is, or a spot for this camera to go that is 2 feet wide. So if you can visualize a 2-foot wide area around the entire track, that would be 2 feet. So if you see the green circle, we would consider the inside circle, and the blue circle we would consider the outside circle. What would the radius of the outside circle be? Well, we have 8 for the inner circle, and then we have the 2 extra added on for the outside circle, so that would be 10. Now our goal is, how much further does a wheel go on the blue circle than it does on the green circle? So since we're talking about distance around the circle, we're not talking about area or anything, we're talking about circumference. So first of all, we want to figure out the circumference of the big circle. Okay, so I'll just put circumference of big so I know which one I'm talking about. Well, the circumference is the 2 times pi times r is the one I'll use since we are given the radius, as opposed to the diameter. Now diameter would be pretty quick to figure out, as it just be the radius times 2, but we will take 2 times pi times r. So all I need to do is plug in the radius, which in this case is 10. And if I want to leave it as exact terms, then I would just multiply the 2 times the 10 and leave the pi symbol in there. That would remind me that it would be 20 pi, and the answer is not 20, that's not your circumference, but it's 20 times pi, whatever that number would be. But instead of rounding in the middle of the problem, I want to leave it exact, so that way my answer will be exact in the final answer, as opposed to just the intermediate answer like we've talked about a little bit in class. So that's the circumference of the big circle. That's how much the camera would go around if it went around the blue circle. Now we want to figure out, the question is, how much further does it go on the outer rail around the blue circle than it would around the green circle? So now we want to figure out the circumference of the smaller circle. So I'll put circumference of small to keep me sure of what I'm talking about here. Same formula, 2 times pi times r. 2 times pi, well, the circumference of the radius, of the inner circle is 8, so I plug that in. Keep that all exact. 8 times 2 is 16, and I'll leave the pi symbol there, so that's 16 pi. Now, the last step in this problem is to figure out how much further it goes around this circle than it does around this circle. So some of you might have already guessed this, but in order to figure that out, we will take the circumference of the big circle and subtract that from the circumference of the smaller circle. So when we take 20 pi minus 16 pi, we would be left with 4 pi. Or, if it asks you to round, that'd be approximately 12.6 feet. Since we're just talking about a linear distance, the unit on that will be feet and not feet squared or square feet, as more people might say, unfortunately for some of you. Alrighty, so on to the next thing. If you need to go back, once again, you can rewind that. We've talked about arc measure, and we talked about arc measure in degrees, but now we want to talk about the length, actual length of an arc. And I know it's kind of confusing to talk about length of a circular object, but we talk about length of a circumference. If you would think about rolling the circle out on edge, kind of on edge, then that would be the circumference or the length around the circle. So when we're talking about an arc, we're talking about a portion of that circumference. So arc length is a fraction of the circumference. Okay, so on this drawing right here, if I'm trying to figure out, I'm not trying to figure out the measure anymore, I'm trying to figure out the length of AB, sorry. The length of arc AB is equal to, well, we have to know the measure of that arc, okay, which once again will correspond to this central angle. So if this central angle was 50, for instance, then the measure in degrees of this arc would be 50 degrees. So once we know the measurement of that arc, then we take that divided by 360, and then we multiply it by the circumference. So this part of our formula right here will give us a fraction, or whatever the fraction of the circle is, and then we'll multiply that by whatever the entire circumference is, and that will give us the arc length as opposed to the arc measure. Okay, so that might be a little confusing. Let's do a couple examples and see if that might help. Alright, so the first one asks us to figure out the length of xy. So hopefully we've been clear on, if we're talking about xy, then we're going this direction, because if we wanted to go the other direction, then we would put the letter P in between that, as will be the case on the next example that you'll see. But in order to know, and in order to figure out what the measure of this arc is, I have to know what the measure of that arc is in degrees. So if I know this part right here is 240, then to figure out what this red part is right here, the interested arc, I know a full circle is 360 minus that 240, and that would give me 120. That's the measure for that arc. So to figure out the length of xy, and hopefully you have room on your paper to do this, I hope you should, we have to take the measure of that arc divided by 360. So that should be a little more arc like times, hold on, let me erase this and write that again. That's a little interesting. Divided by 360, that looks better, times 2 times pi times r. Okay, so all we do now is we plug stuff into our formula. So the measure of arc xy, that's the degree measure. Well, we figured that out to be 120. So we have 120 divided by 360 times 2 times pi times the radius of the circle is from the center to the outside times 15. Okay, so once we get it to this stage, all we need to do is plug it into our calculator. Now the key part here in the directions is where it says leave your answers in terms of pi. So on your final answer, pi should still be in your answer. So what we want to do is we want to take 120 divided by 360 times 2 times 15. Remember, multiplication is commutative, so we can multiply in any order. When we do it like that and leave the pi out, then we're going to get a number, 120 divided by 360 times 2 times 15. We'll get a whole number, and in this case it would be 10. But then you do not want to forget about the pi. You still have to multiply it by pi. We just don't want to multiply it by pi yet, because then it would be a irrational number, and then we'd have to round. Whereas it says we want to leave it in terms of pi up here. So that would be 10 pi, and the unit on that would be centimeters, because we're talking about a length as opposed to an area. So leave the pi out, multiply everything else but the pi, and then at the very end you're going to put that back in there as pi, so to leave it in terms of pi as the directions ask. And that's kind of confusing. We'll try example 2 and see if that helps, and if you are still struggling with that, be sure to ask tomorrow when you get to class. Alright, I've erased that and make a little room for myself. So this example we are trying to figure out what, and I apologize, there should be letter P there, point P on the circle there. That one didn't make much sense without that there, so we'll put the P there, somewhere around there, and our goal is to figure out what the length of XPY is. Alright, so there's not much information that they tell us, or that we're given, in terms of what the measure of these arcs are, but this right here, this is a central angle here, since the vertex of the angle is at the center of the circle, and that tells us that's a right angle. So what is the measure of this arc? That would be 90 degrees, if I can write it. Okay, so if that part is 90 right there, well, the rest of the circle would be 360 minus 90, which would be 270 degrees. So we know that the arc XPY, or the part we're interested in, the measure of that arc is 270 degrees. So to figure out the length of XPY, that arc, we have to figure out the measure, which we already did, we hope, divided by 360 times the circumference. Because once again, this part right here is going to give us a fraction of the circle, and then we're going to multiply that by the length around the entire circle. So the measure of XPY we said was 270 divided by 360 times 2 times pi times 8. Once again, leave in terms of pi, so we'll take 270 divided by 360 times 2 times 8, and we get 12. Get back to the pen here. 12, and then we don't want to forget about the pi at the end, 12 pi inches, since we're talking about a distance. Alright, so that's how we do that problem. I believe that is it for the notes that you have, so we'll call that a video. If you have questions, make sure you ask tomorrow, and have a nice evening, and we'll work on our homework when we get to class tomorrow.